In this lecture, we have to study another sorting technique in data structure, and that technique is heap sort. Heap sort is a comparison-based sorting technique that is based on binary heap data structure. And it is similar to selection sort, where we first find the maximum element, the largest element, and we place that largest element at the end of the array. And we repeat the same process for the remaining elements that we do in the selection sort. Okay. Now, what is this binary heap? Binary heap is a complete binary tree. And what is this complete binary tree? A complete binary tree is a tree in which every level except possibly the last level is completely filled, and all nodes are as far left as possible. Okay, suppose we have 7 nodes in a tree, and we have to create the complete binary tree. We will follow the approach like this. Node number 1 will be placed here, as it has no left and right child, so it is a complete binary tree. Now if we have 2 more nodes, then we have to add here number 2 and number 3 node to the right position, and then if we have to add one more node, we have to add at this position. Okay, at towards the left side of the our nodes. Fine. And if we have to add one more node, we have to complete this level first, number 5. Okay, if we have to add the 6th node, we will add it here, and if we have one more node, we will add to this position. So this is a complete binary tree. Here you see this level is completely filled, this level is completely filled, and this level is also completely filled. Okay, now suppose if we want to add one more node, we cannot add that node to this position. Okay, we have to add that node at this position. Fine. So that is what we say, that as far left as possible. Okay, so this is a complete example of complete binary tree. And in the binary heap, that is a complete binary tree, where we store the items in special order such that the value of the parent node is greater than or smaller than the values of its 2 children. Okay, we have a parent node. The value of this parent node, it can either be greater or less than its children node. Okay, and when this parent node is having a value greater than its children nodes, then this will be called as max heap. And if the value of the parent node is less than its children nodes, then it is called as min heap. Okay, and the heap can be represented as binary tree or array. Now the question is, why array based representation for binary heaps? Since binary heap is a complete binary tree and it can easily be represented as an array, and the array based representation is considered as space efficient. And suppose if the parent node is at some index I in the array representation, then we can calculate left and right children of this parent node by using the formula 2 into I plus 1 and right child as 2 into I plus 2. But here we have a condition that the array should start at index 0. And suppose if the array is starting at index 1, then this entity will not be included here. Then the formula is only 2 into I for left child and 2 into I plus 1 for right child. Okay, and this is for the array when the indexing starts from 1, but when the indexing starts from 0, then we have these formula. Okay, suppose I will take an example here to see how the left and right child of a parent node can be found. Suppose this is an array representation of a heap. It has indexing as 0, 1, 2, 3, 4, 5 and 6. Suppose the elements are 9, 5, 6, 11, 3, 21 and 30. Okay, and now if we want to find the left and right child of suppose this is a parent node and we have to find left and right child of it, we have the formula left child can be found as 2 into I. 2 into I is the index of this parent node is 0 plus 1. Okay, what we have 1, that index 1. This is the left child of 9. Okay, and for right child we have the formula 2 into index I, that is 0 plus 2, that is 2. So this is the right child at index 2 for this 9. Okay, so we can build the binary tree as this. 9 will be placed here. Okay, then we have left child and we have right child. Okay, left child is 5 and right child is 6. Indexing of this 9 is 0, this is having 1 and this is having 2. Fine. Now next we have to find the left and right child of 5 and 6. Okay, and we have to use the same formula. Now for 5 as parent node, what we have to do is we have to find left child of 5. Okay, so left child of 5 can be found as 2 into index value, that is 1 plus 1, that is equal to 3. So 3 would be the left child, that is at index 3. Okay, and the right child of root 5 is equal to 2 into 2, sorry, 2 into 1 plus 2, that is at index 4. Okay, this is going to be the right child of 5. So left child of 5 will have value 11 and right child of 5 will have value 3. Okay, so indexing here will be as 3 and 4. Similarly, now for the node this, that is 6, this we have to find the left and right child. So left of 6 will be found as 2 into index value, that is 2 plus 1 equal to index 5, and right of 6 will be found as 2 into index value 2 plus 2 is equal to 6. So the value at index 5 and at index 6 will be representing left and right child of this parent node. Okay, so here we will be having 21 and here we will be having 30. Okay, so this is how this binary tree, complete binary tree, can be represented in this array. Okay, this is the array representation of this binary tree. Fine. Now the algorithmic steps for heap sort are: build a max heap from input data. We will be given some unsorted input data, and out of that data we have to build a max heap. And at this point what we can say that the largest item is stored at the root of the heap, as we have built the max heap out of the unsorted data, and in that case the largest item will appear at the root of the heap, and we have to replace that root with the last item of the heap. Okay, what we do is we extract the element from that max heap. Okay, and we replace the root with the last item of the heap, that is the last element of the heap, followed by reducing the size of the heap by 1. And when we replace the root with the last item, we reduce the size of the heap by 1 also. And finally we heapify the root of the tree. Heapify means we rearrange the elements, and at the root of the tree we will have the largest value in the unsorted values. Okay, we repeat the step 2 while the size of the heap is greater than 1. That means we repeat this step 2 until we have at least two elements in the unsorted array or in the unsorted heap. Okay, these are the three steps that we have to follow. I will take an example for a better understanding of these statements. Now the question is how to build the heap. We can use the Heapify procedure that can be applied to a node if its children are already heapified. For example, we have a tree like this. Here we have this index 0, 1, 2, 3, 4, 5 and 6. Okay, and we have to start from the bottom and we have to use the bottom up approach. We will start from this last node and we will start the Heapify procedure from this node. Okay, we can apply Heapify procedure on a node whose children are already heapified. Okay, and as these nodes like this 3, 4, 5 and 6, they are the leaf nodes and they are considered as already heapified. So we will start our Heapify procedure from this node. Okay, that is the not a leaf node but the largest node without the leaf nodes. Okay, and we can get this node by using a formula that is n by 2 minus 1 when we start our array indexing from 0. Okay, here we have the value of n as 7. We have 7 nodes. So 7 by 2 minus 1. Okay, and we will take the floor value of this. 7 by 2 will give you 3 minus 1, which is equal to 2. So we have to apply our method from this node. We have to apply Heapify from this node, then we will come to this node and finally we will apply the Heapify method to this node. Okay, this is how we build the heap by using the Heapify method. Now for example, we are given with the input data as 9, 5, 11, 3, 21 and 6. Let's take another element, say we take here 4. Okay, and this is the input data. The indexing is like 0, 1, 2, 3, 4, 5 and 6. So in total we have 7 elements in this given input data, and if we represent this data in the form of a complete binary tree, so that can be represented as, suppose the indexing is 0, 1, 2, 3, 4, 5 and 6. Total we have 7 nodes, and we have represented this data in the array form and we are given with this tree structure. Okay, so here what we do is, first of all we start from its leaf nodes. Okay, as these are the leaf nodes and we consider them as the already heapified nodes. Okay, and now we start from the largest node other than the leaf nodes, that is this node. Okay, and we have to apply Heapify procedure on this node. We see that the root value is 11 and that is greater than both of its children, that is this value and this value. So it is already heapified. Now we will move to this node that is at index 1. Okay, and here we see the value of right child, that is 21, is greater than its parent node. So what we have to do here is we have to exchange these values. So 21 will go here and 5 will come to this place. Okay, so after exchanging we will get 21 here and 5 will come to this place. Okay, and now we will see the next tree, that is this one. Okay, so we have to see this tree. Here we see this is the parent node and this is the left child, this is the right child. What we see here is both the children left and right having greater values than their parent. Okay, so what we will do is we will take the greater value, that is 21, and here 21 will go up and 9 will come down. Okay, so after exchanging these values we will get 21 here and 9 will come to this place. So now this is what we call as max heap. Okay, we have applied the Heapify procedure and we have got this max heap. And now when we represent this max heap in the form of an array, then we are going to get the data as this. The indices are 0, 1, 2, 3, 4, 5 and 6. Total 7 elements. This is the array. So when we represent this tree here in this array, so 21 will come here, 9, 11, 3, 5, 6 and 4. This is the data that is representing our max heap. We have completed the first point of our algorithm, that says first we have to build the max heap. We have already built that max heap. Now at this point what we see that the largest item is stored at the root of the heap as per the point number second. So largest item or the element in the unsorted array that is stored at the as the root of this tree. Okay, that we can see from this tree. Fine. And now as per the point number 2 of this algorithm, what we have to do is we have to replace it with the last item of the heap, followed by reducing the size of the heap by 1, and finally we have to heapify the root of tree. Okay, we have to replace this first value that is at root position with the last value of this tree. This 4 is your last value in this tree. So we have to replace the root value this with the value of the last element. So we have to write here 4. Okay, and 21 should go to this place. Fine. And after that what we do is we heapify the heap again without considering this one element. Okay, so rest of this tree will be again heapified. Heapified means we rearrange the elements and we put the largest element at the root position. Okay, now from this tree I will remove this, as for the next iteration we have to reduce the size for size by 1, and we have to heapify it again. And as this is our root node and we see here the root node is having lesser value than its children, so what we see here, we see here the right child of this root is having 11 value that will go to this position when we apply heapify here, and this 4 will come down. Okay, so after exchanging what we get 4 at this position and 11 at this position. And now when we see this tree again, it is a max heap again. Fine. And all these changes should reflect in the array here also. So after deleting this root value, and here we have to replace this root value with the last element, that is 4. So 4 will come to this place and 21 go to this last place. But now the size of the heap is reduced. So from this point to this point is our new heap. Fine. And after that, by using the formula for left child as 2 into I plus 1, we will calculate the left child of 4 as 9. 2 into index, that is 2 into 0, index value is 0. This will become 0 plus 1, that is the left child will be at this position, and right child will be given as 2 into I plus 2, which is giving you this position. So this is the right child of 4 and this is the left child. So here right child is 11, and what we see, this right child is greater than the root, then we will exchange this right child value and this root value. Okay, so after exchange what we will get 4 at this place and 11 will be at this place. So this is what shown in this tree here. Okay, now we again have to delete this root node or replace this root node with the last element. Fine. Which is the last element? This one is the last element. Okay, so we have to replace the root with the last element, and after replacing, what we will get here and here, 6 will come to this place and 11 will go to this place. Okay, and the same changes will reflect in the array. So 6 will come to this place and 11 will go to this place. Fine. 6 and 11 will be placed like this. Fine. And now again, what we see here, this is the root and we have to find its children. This is the left child, this is the right child. Okay, we see this left child is having value greater than its root, so we have to exchange these elements. So 6 will come to this place and 9 will go up in order to meet the properties of max heap. So after exchanging 9 and 6, we will have 6 here and 9 here. Okay, so here again we have to exchange 6 and 9 in the array. So 9 will come to this place and 6 will go to this place. Fine. And now what we have to do is we have to see the root and we have to delete this root, or we have to, no, before that the size of our this heap is reduced by 1, so I will not include this node here again. So new size of the heap will be from this point to this point, that is again reduced by 1. Okay, and now again we have to replace the value at root with the last element of this heap. So last element here is this one. Okay, so this root will be having value 5 and 9 will occupy this value, this place, that is at 4th index. So 9 will go to this place and 5 will come to root position. Okay, so we have to exchange these two, 9 and 5. So 5 will come to this point and 9 will go to this position. Okay, and now again what we have to find, we have to find the left and right child of this element which is at root position. So this is the left child and this is the right child. Here what we see, the left child is having greater value, so we have to exchange 6 and 5 also. So after exchange, 6 will occupy this position and 5 will go to this position. So similarly here we have to exchange these two values. 6 will come to this position and 5 will come to this position. Fine. And now as per the point number 2 of our algorithm, what we have to do is we have to reduce the size of this heap by 1. So I will remove this node from this tree. Okay, and also our reduced size in the array would be up to this position. Fine. And now again what we see at root position we have the item as 6 and we have to replace this 6 with the last element, that is 3 in the tree. Okay, so we will exchange this 6 and 3. So 6 will come down to this position and 3 will be occupying this position. Okay, and similarly 6 and 3 will be exchanged here in the array. Okay, so 6 and 3 will be exchanged, and after exchange 3 will come to this position and 6 will go to this position. Fine. And now the size of this tree will be reduced by 1. So in this tree I will remove this node at index 3, and also here in the array the new size will be given up to this position. Fine. And now what we have to do is we have to heapify this tree. Okay, and when we see in this tree the value of left and right child is greater than the root, So bigger value is here, is in the left child, that is 5. So 5 will go up and 3 will come down. Okay, so we have to exchange these elements in order to meet the properties of max heap. So after exchange, 5 will be going up and 3 will come down. So here what we will write, 5 and 3 will be written here. So what we have to do is we have to exchange 5 and 3. So 5 will come to this place and 3 will go to this place. Okay, now the left and right child of 5 are having value less than root. So what we will do is we will replace the value of root with the last item in this tree. Okay, that is 4. So after doing that, 4 will be placed here and 5 will come to this place. So 4 and 5 will be exchanged here also. So after exchange, 4 will be placed here and 5 will go to this place. Fine. And after that, what we have to do is we have to reduce the size by 1 as per point number 2 in the algorithm. So I will delete this in the tree. So after deleting, what we have, this is the remaining tree, and here also the updated size of the array would be up to this position. Fine, you see from this point to this point it is being sorted, and now we have to sort the remaining elements of this heap. Okay, and when we see this tree here, we find that the value at root position is greater than its left child, as we have only one child here, and then it is already heapified. So what we have to do is we have to replace the value at root position with the last element of the tree. So after doing that, what we will get, 3 will occupy this position and 4 will go to this position. Okay, and similarly in this array we have to exchange these elements, and after exchanging, what we will get, 3 will come to this place and 4 will go to this place. Okay, and now what we have to do is we have to reduce the size of this tree by 1 as per our point number 2 in the algorithm. So I will delete this here, and also what I will do is I will update the size of remaining unsorted max heap as this. So this is the remaining tree. Okay, and now as we find that there is a single element in the tree and also in this array, so a single element is always considered as the sorted array. So this is how we got a sorted list of array by using the heap sort method, and here we have used heap sort, and under that we have used heapify method. So this is how we get the sorted list of elements by using heap sort algorithm. Now I will write the method that we will be using in our program for the implementation of this heap sort. So here I will write that method, that is max heapify. We'll pass a, that is array, and that is size of array, and we will take a variable I also. This is the procedure for building the max heap, the heapify procedure. And as I said that we have to start from the bottom, and we have to take the bottom up approach in our tree. And let us take the same example that we have just seen, and we will apply this this algorithm that I have written on this page on the left side. We will examine on the same example how this works. The unsorted given array is like this. This is the given unsorted array, and we have to sort this array by using max heap method. And let me create the tree of this given array. The elements are 9, 5, 11, 3, 21, 6 and 4. Okay, so when we call this procedure, we pass here in this procedure array. size of array, that is 7 in our case, and the value I, where we have to apply the heap sort method. Okay, and for that we have to write another heap sort code where we will pass this value I, and that I will write here. Now, as in the algorithm, I have said that we will start our Heapify method from this node for this particular example, because these are the leaf nodes, and all these leaf nodes, they are considered as already heapified. So our procedure will start from this position, that is at index 2. Okay, so you come to this point on the right side here. From this statement, first of all, in the main program we will call the heap sort algorithm, this one. Okay, and we will pass here as argument the array and the size of the array. Okay, in our case the size is 7. Okay, the value of n is 7 in our case, so n equal to 7 will be passed. Fine. And then what we take next, we take here an integer variable, and that is I, and it is a loop control variable, and I will be having value equal to n by 2 minus 1, and we have to take the floor value because this is I is declared as integer. So n by 2 minus 1, n by 2 minus 1 will give us 7 by 2 minus 1, that is equal to 3 minus 1 equal to 2. So I will be having value 2, I will be equal to 2. Okay, and we will check this condition, I is greater than equal to 0, yes, true. And then we call max heapify, we pass here array, size of the array, that is 7, and I is having value 2. Okay, so we will jump from this point to this point. Okay, and here this max heapify procedure is called. Fine, I will remove these arrows, and now I is value equal to 2. So here I is having value 2. Okay, n is having value 7, and we have passed the array. And now what we do here is we here calculate left equal to 2 into I, 2 into 2, 2 into 2 plus 1, that is 5, and right is calculated as 6. So we have seen here the left child is this and right child is this, has been calculated here. Okay, and then what we check next here in this statement, if left is less than n, yes, left is less than n, left is having value 5, yes, it is less than 7, that's true. Okay, this left is less than 7, and a of left is this, a of left is this, that is 6, is greater than a of max. Okay, we have already assigned max, max and I is pointing this position, and max is also this. Okay, I is assigned 2, that is index 2, and max is also assigned index 2. Okay, I and max are here. And then next condition is a of left is greater than a of max, a of left is this, a of max, no, this is not true, so this will not work. Then we come to next condition, next if condition, this one. Okay, right is less than n, yes, right is less than n, right is 6, right is 6, it is less than 7. Okay, that's true. And next condition, a of right, a of right is having value 4. Okay, that is greater than max, yeah, no, this is again not true. So we will come down and we will check next condition, that is at this point, if max is not equal to I, if max is not equal to I, no, this is, here we see max and I having equal values, so this will also be not true. Okay, we do not have to exchange this. Fine, and what we have to do is we will come out of even this if loop. okay, and we will go back to where it was already called. Now we again come back to this for loop from where we had already started this Heapify, and here again the value of I will get decremented, and new value of I would be equal to I minus 1, that is 1, okay, and then again this max Heapify method will be called, and the control will go to this Heapify procedure, okay. But now this time the value of n remains 7, and value of I is 1, okay, and this value of I 1 is assigned to this max variable. So max and I are having value 1, okay, and next in this procedure we calculate left, and left is calculated as 2 into I plus 1, that is 2 into 1 plus 1, which will give us value 3, and right is equal to value 4. Fine, then we will check this first if condition. If left is less than n, yes, that's true, and if a of left that is a of 3, which is this element at index 3, is greater than a of max is this element which is having value 5, no, that's not true. So this if condition will not work. Then we will come down, and next if condition will be checked. We will check if right is less than n, yes, right is 4, n is 7, so this right is less than n, and a of right, a of 4, that is this element, if it is greater than max, yes, that's true, 21 is greater than a of max. Fine, so what we have to do is max is equal to right is having value 4. Fine, so max will be having value 4, so max will be updated, and now max will have value equal to 4, and max is no more having this value 1, but I is still having this value 1, okay, and max is having value 4, so I can write max is having value this 4. Then when we come down and we will reach here, we will check this condition. If max is not equal to I, yes, that's true, because max is having value 4 and I is having value 1. So in that case these two are not equal. Then what we have to do, we have to exchange a of I and a of max. A of I is this element, that is number 5, and a of max is this element, that is 20. We have to exchange these two elements, and after exchanging we will get 21 here, and 5 will come down to 21's place. And then what we will do is we again call this Heapify method, and now the parameters are passed as array, value of n that is 7, and the max is 4. Fine, and this time when we go up, and here we will have this n value as 7 and I value as 4, okay, and let me remove all this what I have written here, okay, and now the value of I is 4, and this 4 will be assigned to this max, okay, max and I are having value I, so I is having value 4 and max is having value 4. So I will write these things here also. I is equal to 4 and max is equal to 4. Then we come down and we calculate left is equal to 2 into I, that is 8, 2 into 4 8 plus 1, that is 9, and right is equal to 10. We do not have 9 and 10 index in our case in this example, so this condition will fail. Then next if condition will also fail, and then we see if max is not equal to I, okay, and this is also not true because max and I having same value, that is 4. Okay, we will come out of this if condition also, and again we go back to the for loop on the right side here again. Okay, so let me remove this extra stuff written here. Now we come back again to this for loop, and here again I is decremented. Now I will become 0, I is decremented by 1, and again this heapify method will be called with a new value of I, that is 0. So here n will be having value 7, I will be having value 0 this time. Okay, and this 0 value will be assigned to max. Fine, so I equal to 0 and max equal to 0. Fine, and then we have to calculate left from this statement as 2 into 0, 2 into I, that means 2 into 0 plus 1. So left will be 1 and right will be 2, and then we will come to this if condition. Then left is less than n will be checked. Yes, it is true, left is 1, that is less than 7, and a of left is greater than a of max. A of left means a of 1, this item. Okay, and is it greater than a of max? Okay, a of max is this one, 9. Yes, it is true. Okay, then max equal to left, so max will having value 1, max will be updated as 1. Fine, then we will check the next condition, that is if right is less than n. Yes, right is having value 2 and it is less than n, and a of right is greater than a of max. A of right means a of 2, that is this 11. Okay, is it greater than a of max? Max is having value 1, a of 1, is it greater than this 21? No, that's not true, this will not work. And then we come down and we will check third if condition. If max is not equal to I, okay, yes, max is 1 and I is having value 0, this is not, max is not equal to I, this condition is true, then we have to exchange the contents ai and a max. Okay, ai means a of 0, this is ai, and a max is a1, this is a max. So 9 and 21 will get exchanged, so we have to exchange 9 and 21. 21 will go to this position and 9 will come to this position. Okay, and now we come down and we will reach to this statement. Here again what we do is we again call max heapify with the new value of max, and that is 1 in this case. Okay, max is having value 1, so this procedure is again called, and here the value of I this time is 1. Okay, and now let me again remove this all stuff that I have written here. Now the new value of I is 1, and this value of I will be assigned to the max variable. So I equal to 1 and max equal to 1. So next statement we calculate left. Left is 2 into 1 plus 1, that is 3, and r is equal to 4. And now we will come to this first if condition, and we will check if left is less than n. Left is 3, yes, it is less than n, and a of left is greater than a of max. A of 3, that is this element, is it greater than a of max? Okay, max is, a of max is this 9. No, this is not true and this will not work. We will come to next if condition, and here right is less than n. Right is 4, yes, it is less than n, and a of right is greater than a of max. A of right means a of 4, that is this element. Okay, is it greater than a of max? A of max is this element. No, that's not true. So this will also not work. Fine. And we will come down and we will reach to this if statement. And if max is not equal to I, then these two statements will work. But max equal to I, so this is also not true. So this will not work, and we will come back to the original for loop that is here. Okay, and now the value of I had become 1 here, and now the new value of I had already become 1, and now when we come to this for loop, here we have to decrement the value of I. So new value of I will be equal to 0 again, and then we call this max heapify procedure here with the new value of I is 0. So this time n will be having value 7, I will be having value 0, and this 0 will be assigned to max. So this time I and max will have value 0. So I equal to 0 and max equal to 0. And we will calculate left equal to 1 and right equal to 2. Okay, this condition will be checked after that, and this condition will also be checked. This is true, left is less than 7, that's true. A of left, that is a of 1. A of 1 is this element, that is 9. Is 9 greater than a of max? A of max is 21. Okay, a of max is 21. No, that's not true. So this will not work. Then we will go to next if condition. In the next if condition, if right is less than n, right is less than n, yes, it's true. And if a of right means a of 2, that is 11. Is 11 greater than a of max? A of max means 21. No, this is not true. So this will also not work, and we will come down to this position. If max is not equal to I, but max is equal to I, they both have same value, so this is also not true, and these two statements will not work. We will again come back to the original for loop, that is at this position. Okay, and we have to decrement I. Fine. And before that I will remove all this stuff. Now we have reached at this place, and I will be decremented again, and new value of I is -1. When this -1 is assigned to I, this condition fails here, because this loop will run up to the value of I equal to 0, and after that, this step, what we have this tree. Okay, and this tree is represented in this above array, and this represents your max heap. Now next step is, what we have to do is we have to remove the value of root node at this position, and we have to place the value of the last node, that is this node, that is at 6th index 4 at the root node. So 4 will go up and 21 will come down to 4 position, and all this happen with the help of these lines of code. Okay, so I will leave this, you do the practice further, and you will understand how this actually happens. And each time when we are replacing element at the root, after that we again call the Heapify procedure. Why Heapify procedure? Because we have to keep the larger node, or the node with largest value at the root node, in order to meet the properties of heap sort. And at this point our this heap is has become as max heap, as it satisfies the properties of max heap. We can see that the largest value has come to this root position, and this here ends our procedure of building the max heap up to this position. Now for these statements are written to exchange the values that is pointed by a of 0 and a of I. Okay, now I will not do the dry run of this particular loop. I will leave this particular loop that is from this point to this point for you, that you will do a practice and you will understand. Now what we have to do is we have to exchange the contents pointed by the last element and the root element. Okay, and also we have to reduce the size of our heap by 1. So here I minus minus is reducing the size of our heap for in every iteration, and what we are doing is we are starting from the last element, that is n minus 7, which is our this sixth index. Okay, and it will go up to 0th index, that is this one in our this tree. Okay, and what we have to do is, as we have built this max heap and now we have to remove this element from the root, and we have to place here this last element, that is 4, and this 21 will go to this position, and we will again reduce the size of this heap by 1. That is what I am doing in this line of code. We are just removing the root element and we are placing that root element at this position, that is the last element, and we are placing this last element at the root position, and then we are decreasing the size of this by 1. Okay, and after doing that, what we have to do is we have to again heapify the remaining heap, yeah, remaining tree. Okay, and that is done by this statement. Heapify means we have to keep the largest value at the root point. Okay, and this is how this max heap works, and this heap sort works in order to sort the elements in ascending order. Okay, and I leave this small task for you. You will go through this loop and you will do the dry run and you will sort the elements. Now after building this max heap, now the array would be something different, and the new entries would be like here we will have different values, and the values would be like this: 21, then we will have 9, then we will have 11, and after that we will have 3, then we will have 5, then we will have 6 and 4. So this is what represents our this heap, max heap. Okay, and after that we have to remove the root node, we have to replace the root node with the last element, and we have to reduce the size of our heap by 1 in each iteration. Fine, and now we shall see the time complexity of this algorithm. The time complexity of building the heap is big O of n. The Heapify method have the time complexity as big O of n, and when we have to remove the elements, that is when we actually sort by using these line of code, we have the time complexity as log n. Okay, so in total the time complexity of this heap sort, we can say it is represented as n log n. Fine, this is the time complexity of this algorithm. Okay, and now we shall see the implementation of this algorithm in the compiler. I have written a code for this in the C language, and we will implement it in the compiler. Now I am in my compiler, and here I have written a code for heap sort, and let's examine this code line by line. And here I have written this Heapify procedure that we use for building the max heap. This is what I am showing in the blue color, and here is the heap sort method from which we will call our Heapify method. Okay, and then here we have our main function. Okay, so first of all the execution of this program starts from this main function. Here I am taking two variables I and n, that is of integer type. I is a variable to control the loop, and n is the taken with the intention to declare it as the size of array. So here I am scanning this size of the array. You can give any size of your choice, and here I am declaring this array with size n as of type integer. Okay, and this for loop is used for entering the unsorted elements of the array that we have to sort in our by using heap sort method. Here I am calling a method, a function, that is heap sort, by passing the array and the size of that array as n. Okay, and whatever the result I will obtain from that, we will print that result by taking this loop that will run from 0 to n minus 1, that is one value less than our size, and we will print the values in that array. Okay, so when we call this statement calls the function that is heap sort, and I have written this function over here. This is the heap sort function. Okay, you see void heap sort int a, array is passed as an argument and the size of the array as n. Okay, and here I'm taking two variables of type integer, that is I and temp. Temp is taken to exchange the elements, and I is taken as the control to control the loop. Here I am taking I is equal to n by 2 minus 1. Okay, in our case n is 7 by 2, that will give us the value 3, as we have to take the integer value, minus 1, that is 2. Okay, we will start the heapify method at the node 2. In our case, we will not start the heapify method on the leaf nodes, and it will run up to the value of I equal to 0. Okay, and I minus minus, that is after each iteration we have to decrement I by 1. Then here we call this max heapify procedure by passing array, size of the array, and value of I, that is 2 in this case, in our case that we have just seen in our example. And then this procedure will be called, and it is the same procedure that I have just shown you, and by executing this procedure, we will be able to sort our elements. Fine, and now let's compile this program, and let's see if there are any errors. No, there are zero errors and zero warnings. This is working fine, and let's run this program. Here it is asking me to enter the size of array, so let me enter size as 10. Fine, and enter 10 elements of unsorted array. So let us enter 9, 5, 2, 99, 45, 32. I will enter 2 again, and let's enter 9 again. I will enter 10, and one more element we have to enter. Let's enter 23, and now I will press enter, and you can see that this program has sorted our unsorted list by using the heap sort method. So 2 and 2, I had entered 2 twice in my unsorted list, then 5, then 9, I had entered 9 twice in my unsorted list, then 10, 23, 32, 45. So you see this program has sorted our unsorted list in the ascending order, and we have used the heap sort method. So I hope you have understood this heap sort algorithm, and if you have any queries, you can post them in the comment section. Okay, and thank you for watching.